Okay, well, let's start. It's a pleasure today to have Jean-Luc Margot from the Earth, Planetary, and Space Sciences Department and Physics and Astronomy Department at UCLA. Jean-Luc works on the properties of asteroids and binary asteroids, has worked on Mercury and Venus, and also on exoplanet systems. He got his PhD from Cornell in 1999 and was a postdoc at Arecibo and Caltech before joining the faculty at Cornell, and then moving to UCLA, where he was chair of the department for several years, but has now escaped that task. I guess, I left off of my list. Also works on technosignatures around exoplanet systems, and his honors include the Harold Urey Prize of the AAS Division of Planetary Sciences. And today he is going to tell us about the spin of Venus. And as a reminder, we'll have at 2 o'clock, for those who'd like to get into a more extended follow-up discussion, you can rejoin on this same link. So take it away, Jean-Luc.
All right. Thank you so much for the kind introduction and for the invitation to present. And I want to express my deep gratitude for your willingness to reschedule. I've had a pretty challenging situation with a young child at home, and postponing this talk has really allowed me to finalize some of the results. So thank you for that. So I'd like to tell you about the spin state and the interior and the atmosphere of Venus today. And I thought I would give you an executive summary just in case something terrible happens with Zoom. So I'll be talking about a relatively new Earth-based radar technique called the radar speckle technique, a radar speckle tracking technique that provides instantaneous spin rate measurements with a fractional precisions of 5 parts per million. So that's been transformative. That's what I'll be talking about today. I'll show that we can improve the knowledge of the spin axis orientation by about an order of magnitude in each dimension compared to the Magellan determination. We've determined for the first time the precession of the spin rate of Venus. It's about 44 arc seconds per year. And based on this, we have a first estimate of the moment of inertia of 0.337. It has larger uncertainties, 7% uncertainties that we'd like, but we're on our way to get to better precision. And with that, we can infer a core size of about 3,500 kilometers. We have a new estimate of Venus's spin period, which, as you'll see, the estimates have been discordant so far. And we've also detected substantial variations in the length of day at Venus. We detect a lower bound of 61 parts per million variations in the spin rate, and that's about 20 minutes change in the spin rate of Venus. I'll ascribe those variations to changes in atmospheric angular momentum, and the amount that it takes to explain those variations is something like 3%. We observe possibly a diurnal forcing of these length of day variations, and it's perhaps linked to mountain torques, and I'll describe that later in the talk. And then if we have time, we might touch upon what are the prospects for landing a spacecraft on Venus, and what sort of uncertainties would you be facing right now with our knowledge of the spin state and these length of day variations. And it turns out it's substantial. It's kilometers, and it increases with time. So we have learned an incredible amount from rotation studies of the Earth. We've learned about the interior of the Earth and the interactions between its fluid layers by monitoring the spin state of Earth, both in in magnitude and in direction. And this is a powerful technique because very often we know the forcings and we can observe the response, again, in amplitude and phase, which informs us about important geophysics. And here's a cartoon that describes some of the physical processes that we can observe when monitoring the rotation of the planet. And so our goal is to do the same kind of geophysics with other planetary bodies. This chart has two purposes. The first purpose is to show you that our knowledge of Venus really hasn't changed since 1983 when this cartoon was drawn, and it really is a cartoon. We have no measurements of the moment of inertia of Venus or the size of the core of Venus. And it's our sister planet. It's the planet next door. There are billions of planets like Venus in the galaxy, and we don't even have that fundamental information about our solar system planet. The other aspect of this chart that I want to emphasize is that understanding the interior structure of planets is really important if we want to understand pretty much anything else about these planets. So for instance, the surface geology is an expression of forces going on in the interior of the planet. The atmospheres are result from the history of outgassing from the interior of these planets. The magnetic fields and magnetospheres depend on the interior. In terms of understanding planet formation as well, understanding the internal structure is critical. And also anything having to do with thermal evolution of the planet, which is going to have a significant impact on the evolution of these bodies, or spin evolution or magnetic field evolution, requires understanding the interior structure. Now, when I started these observations, the situation we had with the terrestrial planet is shown here. We had moments of inertia for Earth and Mars, but we didn't know anything about Mercury and Venus. And with the technique that I'm going to be describing today, we observed Mercury, and we were able to show that Mercury is in a Cassini state. We were also able to show that Mercury has a molten core, and in combination with gravitational harmonic coefficients obtained from the MESSENGER mission, we were able to actually measure the moment of inertia and the size of the core of Mercury. And so that's been really satisfying to make progress in understanding the interior structure of Mercury and to be able to derive pressure profiles and density profiles in the interior of this planet. So our goal now is to essentially accomplish the same goal with Venus. So I want to get some notation details out of the way. I'll be talking about moments of inertia, A, B, and C, where C is the largest principal moment of inertia. It's an integral constraint on the distribution of mass inside the body. And the C-axis obviously is the axis about which bodies prefer to rotate when they're in a state of principal axis rotation. And then I'll be talking about coefficients in the spherical harmonic expansion of the gravity field. And really, for Venus, I'll only be talking about J2, the second degree coefficient, which is the difference between the polar and equatorial moment of inertia over mr squared. When we talk about Mercury, I also describe C22, which is the difference between the equatorial moments of inertia, B and A. All right, so how would we go about measuring the spin state of a body with high precision? And I'll illustrate the situation with Earth. One possible way to do it would be to define an inertial frame, a celestial reference frame, based on the positions of distant quasars. And you might also want to define a body-fixed reference frame based on the positions of VLBI stations or GPS stations. And then you would relate these two frames, the celestial reference frame and the terrestrial reference frame, through a combination of rotation matrices shown here. The first one shows a precession and nutation of the celestial pole. The second rotation matrix would include spin variations around the celestial pole. And the third one, polar motion, would represent the fact that the celestial pole pierces the crust at different positions on the surface. So I want to illustrate that first rotation matrix, precession and nutation, because we'll be using this to measure Venus's moment of inertia. You can write the torque equation. So the planetary body is flattened as a result of its rotation. Solar torques result in a precession of the spin. And you can write down the equation for the change in the longitude of the node. It depends on the mass of the perturber, the amount of oblateness, the C minus A. N square, mean motion square, is essentially 1 over A cubed, so a distance factor. Theta is the obliquity. And then in the denominator, we have C omega, which is the spin angular momentum. For Earth, this precession has been measured. It's about 50 arc seconds per year. And because we know all the other quantities in this equation, we can infer the value of C minus A over C, and it's about 1 part in 300. We can then combine this knowledge with the gravity field, the second degree gravity field J2, C minus A over mr squared, which has been measured by tracking the positions of satellites. It's about 10 to the minus 3. And we get a direct measurement of the moment of inertia over Earth, shown here. So let's move on to the second component, spin rate variations, which I'll also consider for Venus. And at Earth, there's a secular change in the length of day.
Sorry, can I ask a question? I got
Sure.
lost. What is this perturber? Sorry, can you go back? What is this?
Oh, I apologize. In the case of the Earth, the primary perturber is actually the moon, which provides a torque that's about twice as strong as the sun. In the case of Venus, we'll consider the sun only.
Okay, thank you.
So the secular evolution of the spin has been documented by the timing of eclipses. So in the sands of Iraq, there are clay tablets that describe the timing of eclipses 2,000 years ago. And on that basis, we've been able to realize that there's a 1.8 millisecond per century change in lengthening in the duration of the day on Earth. Most of that component is related to angular momentum exchange. As the moon recedes from Earth, the spin of the Earth slows down, and we can compute that very accurately. And it turns out that's 2.3 milliseconds. So there's a half millisecond per century difference. And it turns out that that is related to a change in the oblateness of the Earth, essentially post-glacial rebound. Since the deglaciation, the Earth is changing its shape, its moment of inertia is changing, and that results in a speeding up of the length of day by about half a millisecond per century.
So this is really coming apart from eclipse timings. It seems like this would require us to be able to compare to Syrian observations at second precision. Is that?
No, I believe that the difference is hours. It's like 12 hours or something like that if you go back 2,000 years.
Well, so if it's 1.8 milliseconds per century, and it's 20 centuries, that
yes, but there's a quadratic that goes in there, right? You have to integrate to get the rotational phase. So in terms of rotational phase,
I see. Okay,
it's substantial.
Got it. Thank you.
in addition to the secular variations, there are all kinds of variations in the spin rate of the Earth, some of which are illustrated here, which really inform us about a variety of geophysical processes. And one of the things I want to mention is that the largest variation amount, which you can't quite see from this plot, but the largest variations are on the order of 7 or 8 milliseconds. And it turns out there's just not enough angular momentum in the atmosphere and oceans to explain those kinds of length of day variations. And therefore, these long-term, these decadal and larger timescales variations have been ascribed to core mantle interactions. And this chart shows both a measurement of the changes in length of day and some models of core angular momentum variations based on surface observations of the magnetic field. And there's a reasonable agreement. All right, let me finish with the third rotation matrix. And in the case of Venus, I'm actually not going to talk about this, but this cartoon represents Tommy Gould's story of beetles walking around the Earth, illustrating the fact that the distribution of mass on the Earth can change as a result of plate tectonics or glaciations. And the planet responds by pushing the extra mass towards the equator, essentially to maintain this principal axis rotation state. And so there are observed changes in the location of the spin axis with respect to the crust that are actually consistent with patterns in deglaciation. So that's called polar wander. And there's another component to this, which is a wobble that was predicted by Euler after he wrote down the equations for rigid body rotation, and was not discovered for more than 100 years because the period that you predict on the basis of rigid body rotation is not quite the period at which this wobble is observed. And that's because the Earth is not a perfectly rigid body. So we are able to learn about the anelasticity of the mantle by measuring the actual periods and also the time scale at which the wobble dampens. It dampens on decadal time scales, and so it's continually excited by ocean bottom pressure variations and atmospheric variations. So here's a little bit of a summary. I've talked about precession, polar wander, wobble. Here are their time scales and amplitudes and the processes that are invoked and what we can learn about the Earth by studying these variations. And then in terms of length of day, again, all kinds of time scales affecting the rotation spectrum of the Earth due to tides, atmospheric angular momentum variations, El Nino, core mantle torques, and so on and so forth. So there's a wealth of information to be gleaned about the planets from studying their rotation rates. So here's my sort of first summary slide. Rotational dynamics are really powerful in terms of revealing interior properties and processes, including moments of inertia, core mantle interactions, atmospheric angular momentum variations, and even viscoelastic properties of the mantle. And so I think it would behoove us to establish a rotation service for planetary bodies in the same way that we've done for Earth. Let me move on to Venus. Again, our sister planet, of which there are probably billions of cousins in the galaxy. And again, we don't know the size of the core of Venus. And for Earth, I mentioned we've learned about the moment of inertia from spin precession. That's also what's been done at Mars. At Mars, we've had long-lived landers, starting with Viking up to the modern landers. And by combining radio science tracking of these landers over a long period of time, we've been able to measure the spin precession of Mars and derive a moment of inertia as well. Now, the prospects for having long-lived landers on Venus are somewhat tenuous or very tenuous. And the prospects for landing seismometers that are going to survive on Venus are equally tenuous. And so we're really not in a great position to make progress on this question with spacecraft measurements in the near future. So what do we know about the interior of Venus? We know the gravity field very well. That was measured by Magellan to degree 180. We also know the K2 love number. And initially, this value of the K2 love number was interpreted to suggest that the core of Venus is liquid. But there's a recent paper that does very thorough modeling of the interior by Dumoulin et al. That actually shows that there are some models in which the core is solid that are also consistent with the K2 constraint. So we don't know the size of the core of Venus, and we don't really know if the core is liquid or solid. In this paper by Dumoulin et al., they consider a variety of reasonable compositions for the interior of the planet and thermal regimes, and they could calculate the polar moment of inertia, and they obtain a range of values that are shown here. So there's a sufficiently large range at the moment that we would like to be able to rule out some of these models by measuring it directly. And the measurement approach that we're going to be using is the precession of the spin axis that I've described. I've rewritten the equation here. It's essentially the same equation, but I've emphasized different factors. The only perturber that contributes to the precession is the sun. And I've highlighted the J2 here, which previously I had C minus A over MR squared, but I've replaced this with J2 to emphasize the fact that the precession is inversely proportional to C over MR squared, this normalized polar moment of inertia. And again, we know the mean motion very well. We know the spin rate very well. We know the obliquity. We know the J2. So if we can measure the precession rate, we have a direct measurement of the moment of inertia. So here are some of the numerical values. The mean motion corresponding to the 225-day orbit is shown here. The J2 value measured by Magellan observations of the gravity field. I'll present our estimate of the spin rate, omega, and the obliquity, theta, and the value of C over MR squared and the precession rate that we've observed. Now, I want to emphasize that even though this precession rate of 45 arc seconds per century is comparable to Earth's precession rate, Earth is 50 arc seconds per year. I'm sorry, I said century, I meant year. 45 arc seconds per year. There's a big difference, and that's due to the obliquity. So on Earth, the 23-degree obliquity implies that the spin makes a large motion on the sky. At Venus, with the 2-degree obliquity, the motion on the sky is really only 2 arc seconds per century. And that's a difficult measurement to make. It requires a high precision technique, and it requires patience.
Jean-Luc, I have a
Yes.
question. How does how these calculations are affected by the atmospheric tide on Venus? Is this a big factor that you have to account for?
I'll talk about the atmosphere later in the talk. The precession itself is unlikely to be affected by the atmosphere.
But the injection of angular momentum, does it change any calculations that you have to do in this case?
Not for the precession rate itself, but I'll show how the atmospheric angular momentum affects the spin rate of the planet.
Okay, thanks.
So just to summarize, the precession period is about 29,000 years. And the motion on the sky that we're trying to detect is 2 arcseconds per century. So how do we go about measuring this tiny motion? We're using an Earth-based radar technique. We're using the Goldstone 70-meter antenna, which is equipped with a 450 kilowatt transmitter. And we're transmitting a monochromatic wave at 3.5 centimeter wavelength towards Venus. We're transmitting for the entire duration of the round trip light time to Venus. So, as low as 5 minutes and as long as 15 minutes, depending on the distance. And then we're recording the echoes from Venus at Goldstone. And the echo that we get back is speckled. And the reason for the speckles, so if you plot the echo power as a function of time, you observe these this is real data. So these are the variations in echo power that we obtain. And the reason for the speckles is due to the fact that the surface is composed of millions of individual scatterers, all of which respond with their individual amplitude and phase. And so there's constructive and destructive interference. And when you combine all of these signals, you end up with what looks like a random waveform, but it's not random. It's related to the distribution of scatterers on the surface. So the analogy I like to use is not a perfect analogy, is a disco ball, right? We eliminate the disco ball, and disco ball is spinning, and we're getting this speckles. Now, the key ingredient for this technique is that we're also recording with a second distant telescope, in this case, the Green Bank telescope. It's a 100-meter radio telescope in West Virginia. And the speckles, because they're due to the distribution of scatterers on the surface, they are tied to the rotation of the planet. And so these speckles travel on the surface of the Earth. And so I'm showing the same data here that I've shifted by about 20 seconds to align them. And you can see that the two time histories of the radar echoes received at Goldstone and Green Bank are roughly similar, except for receiver noise. The receiver noise is different at the two telescopes, obviously, but the speckles have the same appearance. So that's the technique that we'll be using to learn about the spin state, both the direction and the magnitude of the spin state of Venus. Now, this technique was described in a sense in the early 60s, and we haven't used it for many, many years for reasons that are not entirely clear. So Green, in the early 60s, described these speckles, and he's drawing contours of electric field strength on the receiver plane. So this is the plane of the surface of the Earth, if you will. And he's drawing a receiver 1 over here and receiver 2 over there, showing the trajectory of the speckles along velocity v. And in his paper, he describes the fact that if the speckle trajectory is aligned with the baseline connecting the two telescopes, then the speckles will be highly coherent, they will correlate. And he describes the fact that it's obviously dependent on the spin state of the planet. And he shows that for any baseline delta x, there's a time lag delta t that's going to maximize the correlation of the speckles, and that it depends on the range to the planet r and the spin vector of the planet omega plus the orientation as well. So the first observable that we are using is the epoch at which the speckles correlate. And I want to emphasize they don't correlate all the time, right? So here's t minus 1 hour. The speckle trajectory here does not go over both telescopes. And at that time, the two telescopes essentially receive time series that do not correlate at all. At time t, they correlate, and at time t plus 1 hour, they don't correlate either. The time at which this correlation takes place is a strong constraint on the orientation of the spin axis, because we know the positions of these antennas to centimeter precision. We know the orientation of the Earth to extreme precision as well. And so the time of day at which this happens is essentially a direct measurement of the spin axis orientation. Now, I want to emphasize that we're only sensitive really to one component of the spin vector. So if you imagine the disco ball and the two receivers placed horizontally, if I tilt the disco ball this way, the time at which the correlation is going to take place remains the same. So we're not very sensitive to changes along this axis, but we are extremely sensitive to changes along this axis. So that will produce very narrow error ellipses in our measurements. So let me illustrate an example correlation. This is what happens as a function of time from the data recording start for this particular run. The black is actual data. And as you can see, before the speckles line up with the antenna baseline, there's no correlation. And then there's a dramatic increase in the correlation scores that doesn't last very long. It lasts about 30 seconds. And that's what makes this technique so powerful. The size of the speckles is given by the diffraction formula, R lambda over D. And for Venus, it turns out that the size of these speckles is about 1 kilometer or even less. And remember, the baseline is 3,000 kilometers. So there's only a short amount of time because of Earth's rotation that this 1 kilometer speckle pattern remains aligned with the 3,000 kilometer baseline. And as you know—
Why is the correlation not exactly 0 when you go far away?
Oh, over here? This is— yes, this is because it's a complex correlation of a noisy time series.
Oh, that's just the noise.
So yeah, you're measuring the noise essentially. Yeah.
Thanks.
It depends on the bandwidth and integration time, and it behaves in the way that you would expect for random noise sequences. So the width of this function, the 1 sigma width, is about 10 seconds, but it turns out we can measure the centroid of the peak of the correlation to a fraction of a second, to 0.3 seconds, essentially. And that's what gives us powerful measurements on the orientation of the spin. I'm going to skip— these are tables of measurements that we can come back to if we need to, but I want to illustrate our measurements that we've obtained starting in 2006 all the way to 2020. We have 21 measurements so far. And each one gives us a very narrow error ellipse for the position of the spin axis on the celestial sphere. And they're represented here by a color-coded line that matches the observing date. If I include a precession model, these lines converge nicely into one point of the celestial sphere. The diamond there is our best fit solution. And I'm also showing with this dotted line 100 years worth of precession of the spin axis between 1950 and 2050. So I've referenced my solution to J2000. And the orientation of these lines depends on the aspect at which we observe Venus. So it essentially depends on the ecliptic longitude of the projected baseline, which varies as a function of time. And that's why it's important to measure this effect from a variety of baseline orientations to fully constrain the spin axis orientation.
So these are lines because of what you said earlier, that basically you're measuring one direction and not the other.
Correct.
So you're actually sort of very, very long error ellipses.
That's
but
correct.
But their orientation changes with time. Okay, thanks.
Yep.
So Jean-Luc, here you're just exploring the existence of the speckles. You don't need to know the actual surface topography from, let's say, Magellan observations or anything, right?
That's a great question. Yes, it's completely independent of the distribution of scatterers. All you need is a pattern that repeats. And there's even a theorem that shows that it works for arbitrary topography.
Okay, and then I mean, are you beaming Venus with a continuous beam, or you do, very short pulses and then looking for echoes? I mean, how does the radar actually work?
We do a continuous transmission for the entire round trip light time. Now, I have to be careful about when I transmit and when I receive. So before the observations, I predict when this correlation is going to take place. And I arrange for the transmission to happen before that and to make sure that the event happens during the receive window.
Okay.
So here's our new solution in black for the spin axis orientation of Venus, the 1, 2, 3, and sigma contours. And I'm showing for reference the Magellan solutions from Davies et al. In blue. This was based on analysis of hundreds of landmark positions observed by Magellan over hundreds of days. And the Magellan radar was a really capable radar system with resolution of about 100 meters for 90% of the, more than 90% of the surface. And by solving for they used multiple observations of these hundreds of landmarks to identify the spin axis orientation. And this is the result they obtained. A few years later, Konoplov analyzed several years of observations of radio science observations of Magellan to obtain an independent estimate of the spin axis orientation that is shown in red. And again, I'm showing the precession trajectory here between 1950 and 2050. So one thing to note is that Davies et al. Had 46 arcsecond uncertainties, Konoplov et al. 14 arcsecond uncertainties. We obtained less than 3 arcsecond uncertainties in each dimension. And that corresponds to about 80 meters on the surface. Now, I've precessed the solution to J2000. That's my reference. You can see that my measurements are only really marginally consistent at the 1 sigma level with Konoplov and Davies' measurements. And that's because their measurements refer to the epoch at which they measured the spin axis orientation. So if I precess their measurement to epoch J2000, this is what I obtain. So I'm going to oscillate between the two. Here's the non-precessed version, and here's the precessed version, non-precessed, precessed. So with that precession, the measurements are considerably more consistent. So in my model, I solve for 3 parameters. I have the right ascension and declination of the spin axis, and I have the moment of inertia, essentially. So the solution that I obtain from least squares analysis is shown here. So there's this precession rate, minus 45 arcseconds per year. That is, a direct measurement of C over MR squared. And I was curious to see whether the measurements were robust with respect to inclusion or exclusion of some of these 21 data points. So I ran 2,000 bootstrap resampling cases, and that allows me to quantify the plausible errors. So I get again, about a 7% uncertainty on the measurement of the precession rate and the moment of inertia. Now, again, that's not as precise as I would like to have it. It doesn't currently rule out some of the interior models. But if we continue these measurements, we will improve the precision for two reasons. One, there's a square root of over n type of effect, 1 over square root of n type of effect that will improve the precision. But also, as we take additional measurements, the total amount of spin precession increases at a rate of 2 arcseconds per year. And so we can beat down these errors and ultimately obtain a moment of inertia that's going to allow us to make geophysically meaningful inferences about the interior of Venus. So with our estimate, we can consider a 2-layer model for the interior of Venus with a core and a mantle, and assume an average density for the core and average density for the mantle. We have 2 integral constraints, the bulk density, and now we have a normalized moment of inertia, but we have three unknowns: the density of the mantle, the radius of the core, and the core density. Now, it turns out that all of the interior models that were shown in this paper by Dumoulin et al. Have pretty much the same core density. They're all within 1% of this value over here. So I've adopted this value for the core density and solved for the other 2 parameters. And I find a core radius about 3,500 kilometers, which is 58% of the radius of the planet, and a mantle density that's about 4,000 kilograms per meter cubed, which is 10% smaller than Earth's value, but perfectly acceptable. So I want to emphasize that even though this is not as high precision as we would like, it's not going to get better with spacecraft very easily. So here I'm considering what you could do if you had the Magellan measurement and a new spacecraft. And let's assume that this new spacecraft has infinite precision, can measure the spin axis with 0 arcsecond uncertainties. And this is the red line shown here. And let's assume we have a measurement in 2040. That's 50 years since Magellan. 50 years times 2 arcseconds per year is 100 arcseconds on the sky. But the Magellan measurement has 14 arcsecond errors, uncertainties associated with it. So you get about a 14% uncertainty with 2 spacecraft measurements. And we're already at half that. We already have a 7% uncertainty. So again, the prospects for spacecraft improvement of this quantity are not very good. So I'll summarize this part of the talk. Let's see, how am I doing on time? We've improved the knowledge of Venus's spin axis orientation. We've measured the precession rate, obtained a moment of inertia, and a nominal core size with a current precision of 7%. See, it's 8:42. Okay, so let me then talk about the length of day on Venus. And oddly enough, we don't have great estimates of the length of day on Venus. What we have, the best 3 estimates we have are average measurements, and they're shown here. So the Magellan radar produced an average over a period of 500 days that is shown here. And then by combining Magellan and Venus Express, another team obtained an average value over the 16-year baseline between Magellan and Venus Express that is shown here in red with their error bars. And probably the best we have so far, and I was involved in this effort, is on the basis of 29 years of tracking of radar observations of certain features on the surface. And this is the estimate in green here with the error bars. And again, that's an average rotation rate. So the measurements are not necessarily in great agreement with one another, and they also completely obfuscate the fact that there are variations around these average values. What we do know about Venus is that it has a 243-day retrograde rotation that is unexpected in a sense. If you compute the tidal torques from the sun, Venus should synchronize and should have a orbital period equal to, I'm sorry, a spin period equal to its orbital period. And therefore, we need to explain how it maintains this 243-day retrograde rotation. And the idea was first proposed by Tommy Gold and Steve Soter, that there are atmospheric tides that produce a torque that essentially counteracts the solid body torques. So in this illustration, we have the sun and a mirror image of the sun. Here's the rotation of Venus. The body is elongated, is deformed, and therefore there's a torque that tends to slow down the spin of Venus. But the atmosphere, represented by this outer ellipse here, has a torque in the opposite direction because there's a transfer of mass from the hot parts of the planet to the colder parts of the planet that produces an atmospheric bulge and therefore a torque in the opposite direction. And the hypothesis is that these two torques counteract one another and that Venus settles at a rotation period where the two torques are equal but opposite in direction. So here's a diagram of the strength of the torque. Turns out the solid body torque hardly depends on the spin rate of the planet, but the atmospheric torque is a strong dependence on the spin rate of the planet. And so at present time, we have a retrograde rotation shown here with the diurnal frequency about 117 days. We think that's how it works, but we really have not a great understanding of this process. And in particular, we don't know whether there are variations around this equilibrium, how quickly the planet returns to the equilibrium when it's perturbed from that position. So we're trying to quantify these processes by making measurements of the spin rate and the instantaneous spin rate. I'm coming back to this chart when the speckled trajectory is aligned with the two antennas during those precious 30 seconds. And during that time, we can, of course, measure how long it takes for the speckles to travel from one telescope to the other. And we know that distance exceedingly well. So we get a direct measurement of the spin rate by measuring the time lag for the correlation during those 30 seconds. So here's a correlation plot, this time as a function of time lag. And we can measure the time lag with a precision of something like 0.1 milliseconds, whereas the time lag itself is on the order of 20 seconds. And that's where our 5 parts per million precision comes from, is due to the fact that we can measure this time lag to very high precision. So here are the length of day measurements on those 21 instances between 2006 and 2020. I want to point out that sometimes the measurements occur on consecutive days, but most of the time they do not. So this is not an accurate time representation. This is just a list of all our measurements. And I'm showing for comparison, again, the Magellan estimate of the spin rate shown here, the Magellan plus Venus Express spin rate measurement shown in red, and the Earth-based radar measurement shown in green. So there are a couple of things to note. First of all, the length of day on Venus changes. There's no way to fit a constant spin model to these measurements, and we can rule that out with very high confidence. Also interesting is that most of our measurements are not consistent with any of the previous estimates. They are showing much wider variations than what's illustrated there. We then use a median of all our measurements to estimate the spin rate of Venus. So I have 21 measurements with 5 parts per million precision over a 15-year period. And that allows me to get a new estimate for the length of day on Venus. And again, I've used bootstrap resampling to show that this is a fairly robust estimate. The other thing we want to consider is the total excursion in length of day. And what we find so far is 61 parts per million variations, or about 21 minutes in the length of day. And if we look at consecutive Earth days, on average, we get about 10 parts per million change, or about 4 minutes change in length of day. So we can consider plausible processes for these variations. On Earth, the largest length of day variation.
Wait,
go ahead.
First, for Venus, you said total excursion, which I took to be from sort of bottom to the top of those points, and then Earth, you said consecutive days. So are these are different quantities?
Yeah, so you're correct. The total length of the excursion, you take sort of the minimum to the maximum. But this daily, what I call daily length of the excursion, is on consecutive days. So for instance, between March 14 and March 15 here, this is the change. Mm-hmm. And I have a number of data points where I have 2 consecutive measurements on 2 consecutive Earth days. And I can quantify how much the average length of day is on a 24-hour period.
Okay, so your 0.00 days is, so both of these sets of numbers refer to Venus, neither one to Earth. Sorry, I thought you said the second one was daily variations in the Earth's spin, but it's.
Oh no, my apologies. I meant
both of these are Venus.
I meant Venus length of day variations on a 24-hour timescale.
Good, thank you.
Because the next thing I'm going to do is I'm going to compute whether torques from the core and mantle can actually explain these, right? So we have 4 millisecond change over a 20-year period. For Earth, at Venus, we have 4 minutes over 1 day, right? So you can compute the acceleration of the rate of change in spin, and you find that there's something like a 4 order of magnitude difference between Earth and Venus. And on Earth, we can use the moment of inertia of Earth to compute the torque that's required. And we can assume that if the core of Venus is liquid, and because the moment of inertia is not too dissimilar, we could expect core mantle torques perhaps of the same magnitude, but there's no way that these core mantle torques could explain these kinds of changes for Venus, right? So they're about 5,000 times too small to explain the change in length of day at Venus. And therefore, the most likely physical process is a change in atmospheric angular momentum. We can compute the total angular momentum by integrating the density and the velocity of the winds over the entire atmosphere. Here is one estimate of the amount of angular momentum at Venus. This is the Schubert et al. Estimate. They're actually not, it's not incredibly difficult to find updated modern values of this number, but it's probably of the right order of magnitude. Now, consider a fractional change epsilon in atmospheric angular momentum. If you were to dump all of the Earth's angular momentum into the rotation of the planet, you would change the spin rate or the spin period of the planet by 3 milliseconds. On Venus, it would change by 11 hours. And that's because the total amount of angular momentum in the atmosphere of Venus is 200 times larger than what's on Earth. Or 21 minutes change correspond to an epsilon of about 3%. So it's entirely plausible that atmospheric angular momentum variations can explain what we observe. In fact, on Earth, we've detected atmospheric angular momentum variations of 20 to 30%, right? So that's our explanation for the changes that we observe. And
And
again,
this calculation of angular momentum, that accounts for the superrotation of the atmosphere, right?
can you repeat, please?
Does this calculation of the angular momentum of the atmosphere account for its superrotation?
Yes, it takes the wind profile from the bottom of the atmosphere, where it's essentially 0 meters per second, to the cloud top, where it's about 100 meters per second. But I should point out that we have very few measurements of the wind profiles. And in fact, we have very little information about the dynamics of most of Venus's atmosphere. We have measurements of the cloud tops, but 99% of the mass of the atmosphere is below that. So we're pretty blind when it comes to the internal dynamics of the Venusian atmosphere.
What about the descent probes of Venera stations and of Vega?
Those are the few, right? We have a few of those.
Okay.
Yeah. So we've now measured the moment of inertia. We can compare Earth and Venus. The total planetary angular momentum we can compute, and we can also compute the atmospheric angular momentum. And what's important to realize is that the ratio, the fraction of angular momentum that's contained in the atmosphere for Earth is tiny, right? It's 30 parts per billion. For Venus, it's 0.2%. And the fact that a substantially larger fraction of angular momentum is contained in Venus's atmosphere, that can explain why we can obtain such significant changes in the spin rate of the solid body for a fairly minor change in atmospheric angular momentum. So the next thing I looked at is whether there are potential periodicities. I looked for a secular change, and it's not statistically significant. I can't claim a detection of a secular change in spin rate, but we may very well expect a secular change in the spin rate of Venus, because if the spin is controlled by a thermally driven atmospheric tides, then any change in insolation may affect the spin rate. And with Venus's current eccentricity, the change in insolation is maybe 3% or so. But over a longer time scale, when we consider the long-term average eccentricity of Venus's orbit, it's about 3.5%, then you have insolation changes of the order of 15%. And there's no doubt that such changes would have affected the spin rate of Venus. So it may have had a very interesting spin rate evolution, including potential captures and resonances with Earth and so on and so forth. In any case, here is what I obtained if I fold the data with a semi-diurnal phase period of 58.4 days. And it, your eye wants to believe that there's a possible relationship there, but this would be a very strange mechanism in which the spin rate of the planet would lengthen, or the period would lengthen over a 58-day period, and then abruptly there would be a release of atmospheric angular momentum to spin the planet back up. I don't know of an atmospheric process that can do this. If you do know, please let me know. I'd love to hear about it. So it's certainly intriguing. Now, if I fold the data with a diurnal period, I also obtain something that is plausible. And I should point out, I computed the phase dispersion minimization for these periods, as well as the Lohm Scargill periodograms. And it's barely statistically significant that you might have periodicities here. But nevertheless, it's interesting to consider whether they exist, and we'll probably need more data to confirm this or not. But on a diurnal phase, this is what happens. And what I've shown here are the locations of large mountain, topography, Aphrodite Terra and Beta Regio. And this is the location of these mountains when the sun is directly overhead, essentially. So in the afternoon, for these mountain ranges, the spin rate tends to be a little slower and the spin period tends to be a little larger. And the question is whether the spin rate variations could be due to mountain torques, and I'm running out of time. As you know, Akatsuki detected these phenomenal planetary scale features that are observed in the upper atmosphere of Venus that rotates with, again, a 4-day rotation. But these features are stationary with respect to the solid surface, which rotates underneath with a much slower rate, 243-day, right? 50 or 60 times slower. So these are very intriguing features, and there's been a suggestion that they are in fact related to mountain torques because they tend to develop in the afternoon over these large topographic rises on Venus. There's a paper that tried to use global circulation models to infer whether these mountain torques could affect the spin rate of the planet. And this is obviously something that's very difficult to model because what they do when they model the mountain torques is that they obtain this dramatic drop in atmospheric angular momentum that's obviously not sustainable. And so they detrend it, they remove it, and they obtain the curve that you see here. In any case, they detect something like 2-minute variation due to these atmospheric, due to these mountain torques, whereas we detect something more like 20 minutes. So I'll finish here because I'm past time. I'll just leave these here because I'm out of time. But thank you so much for your attention and questions.
Well, thank you for a riveting talk, both in how you do the measurements and what they might mean. We have a few minutes for questions. So when you say mountain torques, this means basically wind hitting the mountain and exerting a torque?
And it launches the hypothesis is that it launches a gravity wave, and that these waves carry momentum, obviously, and may affect the spin rate.
Okay.
So in the calculation of the change in the spin rate of the planet due to the atmospheric torque, is the planet treated like a solid body, or if it's got a liquid interior, does it necessarily respond instantaneously to torques on the surface throughout the volume? I mean, are you just spinning up the crust and not actually spinning up the whole planet so that the moment of inertia would be quite different?
I suppose it's possible that if the core is liquid, you could have small variations. I don't think they could be very big between the crust and the core.
Okay.
And for Mercury, this is certainly something that we've looked at. But again, we don't really know about the state of the core of Venus.
Is that something that happens on the Earth? Does the crust ever spin differently than the core?
Again, I think very small differential rotation.
Okay.
Could you say something about how Venus got into its current spin state, which of course is quite different from the other terrestrial planets?
Sure. I think the reference paper for that is Correa and Lascar. I believe it's 2003. They had a Nature paper where essentially they postulate that it's the atmospheric torques that got the planet into this state, yeah, I can't reproduce the details right now, but I can send you the reference to that paper if you'd like.
And in their model, is it that it's been in this state for 5 billion years, or they have no idea how long?
I believe quickly after, you know, the atmosphere is formed that the spin changes. They talk about long-term evolution of the spin.
How is angular momentum actually transferred from the atmosphere to the crust? Is this, you know, the near surface boundary layer where you develop a large velocity gradient in the atmosphere that, you know, drives actually the force on the surface? Or is it this, you know, launching of the gravity waves against the surface, well, imperfections, let's say, you know, mountains?
Right. So remember the pressure is something like 90 atmospheres at the bottom, right? So the conditions at the surface atmosphere interface is more like the bottom of the ocean, of a very deep ocean. And the differential velocity, I believe in the first 5 kilometers, yes. There's essentially no differential rotation there between the atmosphere and the planet. According to, again, these very few wind profiles that we have, there's a pretty linear relationship from the top of the atmosphere all the way to about 5 kilometers above the mean surface, but then sort of dropped. So essentially the very little motion between the bottom atmosphere and the crust.
Then this mountain ranges must be above these 5 kilometers to drive.
Some of them are.
I see. Okay.
Right. So I think the features that they detected in Akatsuki are primarily over equatorial ranges that are either above 5 kilometers or most of them above 3 kilometers.
But well, okay, but then so it would be then solely due to these mountain ranges. I mean, the coupling would be affected. Like, how much of this atmospheric tide forcing coming from this bottom 5 kilometers as opposed to the rest of the atmosphere? Is it known?
I don't think that's known. Again, I don't think the wind profiles are very well known. The modeling of the internal dynamics of the atmosphere is very problematic. And that's one of my hopes, actually, is that providing a time history of spin changes may help calibrate these global circulation models.
And obviously, this exchange of angular momentum between different components of the system should lead to some energy dissipation, because, you know, if you're exerting torques, there must be energy dissipation. Is this, I mean, that probably is a tiny contributor to the overall energy budget of the Venusian atmosphere, but still, I mean, has anyone done these calculations, and what would that be?
I'm not aware that somebody has computed the energy release as a result of all of these changes, but I suspect it's small.
Yeah, it's probably small, yeah. Much smaller than the insulation, right?
Okay, well, thank you very much. We'll break now, and anyone who wants to ask further questions is on this or any of the other many subjects Jean-Luc works on is welcome to join us at 2. So thank you very much.
Thank you.